So this will be perhaps a bit shorter lecture than before, but on the end I will try to add some input to the next part of your project assignment to give a conceptual overview of how it fits together. The first part I'm going to talk about is something that you will be using next week. So for this assignment that you have now, that you're working on this week, you will not be able to, you will not use the more advanced mesh generation tools. You will generate your own mesh and topology manually by entering coordinates and assembling. Next week we will, the second assignment will do the use the mesh generation tools that are part of CALFEM as well. So unfortunately, I realized today I missed to translate this lecture, but I will try to translate this in English afterwards, so you can get it in English as well. I will be speaking English, so you can follow along. So what we're going to talk about today is when your problems get a bit bigger, it's very hard to do your mesh yourself. I mean, you can do loops and you can do structure meshes quite easily yourself, but often you have a geometry that is complicated, you have holes, and you also need a lot of elements to get the computational resolution. And to kind of help you generate a mesh from a geometry, there are a lot of tools available that can help you divide your domain into smaller elements. And that is commonly known as mesh generation, or how to connect and generate a lot of connected elements. So, as I said, larger problem, you need to kind of use some kind of algorithms to create your topology. And many of these mesh generation tools, they start from a geometric description. So you describe your problem with lines, splines, circles, and connect them together to surfaces. Or if you're in 3D, you create volumes using surfaces as well, but in 3D. You can also, using these tools and algorithms, you can set boundary conditions on your element mesh. So for example, you can say that only generate elements of a certain size. They shouldn't be larger than a certain size or something like that. You can also explicitly annotate the lines that you say, I want to have at least 10 elements on a certain line. I have a question here from Sarah. You had a question? Volume, I will fix that. Wait a moment. Do you hear me better now? Okay. So as I said, you can specify the number of elements on a certain line. You can also, which we'll not describe in this course, but if you have done a computation already on a mesh, you can use the results from a previous calculation as input to refine your mesh generation. So you can, if you have a large gradient at some point, you can let that be input to make the mesh more dense in those areas. There are two kinds of mesh generation types you can do. You can do structured mesh generation, which means that there is the structure or mesh can be described with a rule. Often you have a coordinate system that you can specify each element, that row, column, and depth or something like that, that exactly specify an element. Usually you can have, for example, you have a cube volume that is like a Minecraft, for example. You can always get to a certain brick by specifying row, column, and depth. Those element mesh generations it's easy to control the generation and the layout, but they are very hard to do if you have very unstructured geometry is complicated. It's very hard to kind of define a structured mesh when you have complicated geometry. And in those cases, you often use something called unstructured mesh generation. And basically what that is a algorithm that takes your geometry and just fills it with elements. It's an algorithm. Usually it starts from the borders and works itself in and fills out the entire domain. And those are available both for 2D and also some 3D geometries. So this is a typical example of a unstructured mesh. So usually it's there is no, you can't find a rule connecting the elements. The rule is that it kind of it should spread out the points and connect the dots together to create the mesh. On the right side, it's a wing surrounded by element. The domain is probably air around the wing. And here you also see that. Let's see if I can just annotate here. So in these areas here around are also denser. And that is probably because they have some kind of rule that says it has to be more elements on the lines, or it could be it has been refined already from a previous calculation. I'll just skip to. Yeah. Structured meshes are shown here in these examples, and here you can see typically there you can see a rule. For example, on the left side here, it's a row column system. So you have rows going like this, and you have columns in this direction here. So you can reach each element by specifying a coordinate in some sense. And the same thing with the other two here. You have a structured mesh here that where you specify that you have, for example, I want 5 elements in this direction here, and you have 3 elements in this direction, and you have 5 elements in this direction here, and it's specified, and then it generates from those rules. And on the right side here, here's a kind of a bit more complicated rule. So you have denser mesh here in the middle, here as well, and it could be that it is some exponential or some kind of rule that defines how the spacing of the mesh element should be. And it's actually not that restricted like you can imagine. So usually when you use structured meshes, you combine, you create a complete mesh by combining several, so to speak, super elements. So in this case here, it's a tunnel section, and you have this is a super element here, which is defined by 4 sides. There is a half circle, lines, and then you specify the number of elements on each border. And then you put them, assemble together like a very coarse finite element mesh. The only rules is that the number of elements here must be the same, so they can fit together. So that it has to be some kind of compatibility rules between these elements. So you can create kind of complex meshes using structured mesh generation, and it's very the good thing with this is they are kind of you know what kind of mesh you will get, and you can refine it parametrically, and it's quite quick to generate a mesh as well. The unstructured mesh generation algorithms can be more heavily computational because the algorithms are more complex and have a different. The more elements, it could be that it takes longer to generate the mesh. What we're going to use in this course is something called a software called GMSH, and it's a well-known, it's open source mesh generator, and it can generate 1D, 2D, 3D element meshes from geometric input. It supports actually a graphical preprocessor and also a graphical post-processor, so you can actually visualize the meshes you generate using this tool. And it can handle both structured and unstructured meshes. And it uses boundary descriptions to define geometry. So you define lines, circles, splines to define your domain. And all these geometries are described in a special language. And we have integrated this tool into CALFEM for Python. And the nice thing with that is that you can do everything from Python. So you don't have to learn the language of GMSH. You only have to learn the interface, that the commands and modules that you have in Python, in CALFEM, to generate the geometry. You have modules. The two main modules is geometry and mesh, which are the first module generates has functions for defining the geometry, and the other one describes the mesh generation tools. So you give the geometry to the mesh generator, and it will generate the arrays that you need to assemble your system. And the nice thing is that what you get out from this mesh is actually arrays that you can use directly in your own code. So you don't have to read output files from GMSH. It is handled silently in the background. So just to make a simple example here, this is a bit from, if you do the groundwater problem, this is the kind of geometry you will have. You have a large domain, and you have this is a wall going down in the ground, and then you have parameters here. And this is also something that is, by using geometric description, it's very easy to generate a parametric model for your finite element code. So, for example, if you want to study the effects of the depth of the wall going down in the ground, you can have a loop that modifies the d values and creates a mesh for different d values. And then you can loop over and do calculation and do a parametric study for something. And that's very easily defined and handled with this mesh generation in CALFEM. So just a quick example. I will show you some live examples as well, so you can see how they're working. But what we need to add now is CALFEM core is the standard CALFEM library. So all the elements and solvers. This is so this here is the geometry module, and we import that as CFG. And then we have the mesh generation module, which has, we import as CFM. So geometry has the routines for defining an object, defining the geometry. The mesh module has mesh generation classes for generating your mesh. So those are the important ones we are going to use. So as I said, it's this kind of mesh generation lends itself very nicely to parametric description. So in this example, we define width, height, thickness, depth as parameters, variables that you can change later on. When we have done that, we can start with geometry. So in this case, this is the key class we're going to use, the geometry class. And we create an instance of this geometry class, and we assign that to a variable j. So j will be kind of the information carrier for our geometry. So on the j variable, we will add points, as in this example here. So we have 0, 0, width 0.0, and we just add them all together. They are numbered implicitly in the order they are created. So if you want to reference them, you reference them in the order you have created the points. So Sarah asked a question about thickness and depth. So the depth is in the So in 2D problem is in the screen. No, sorry. Thickness is in the screen, and depth is the depth of the wall going down into the ground. And we are calculating this as an infinite volume. So it's the depth of the ground, or the wall into the ground, that we will vary. So now we have defined the points. So next we need to connect the points together. And here we reference these are the references to the points. So from 0 to 1, from 1 to 2, to 2 to 3, and so on. And then we then define the geometry. It's very similar to when you create an element mesh by hand, that you reference the different elements by specifying degrees of freedom. But here we define a geometry topology by referencing the indexes of the points. One important thing is that if we want to apply boundary conditions, we need to kind of assign a value that we can reference on the line. So if we go back here again, so in this case here, for the groundwater example, we will have a pressure difference on the lines number 6. So here we will apply water pressure, and here we also have a water pressure that is a boundary condition for this problem. And we need to kind of mark them out in our geometry. So here we have 2 and 6. So you put 80 on the line number 2, and 90 on line number 6. You can also put I usually do a constant for my, so I say that I create a variable in Python with my left side, for example, right side, and assign those a numeric value. And then it's easier to reference them later on. But in this case, we have the markers are 80 and 90. And to finish this off, we create a surface of all of these lines together. That kind of defines our computational domain or mesh we want to mesh. Next, we need to call our mesh generator, and we instantiate a mesh generation object that is called GMSH mesh generator. And here you see that we put in the J here, so the geometry goes into here in this as input, and then we get the mesh generation object out here. And here we can set number of attributes. For example, the element size factor. It's a factor that defines how large the element should be. I think it's related to maximum area of the element. So it's related. So you have to think about how large are elements, and then put the element factor there that is reasonable. You can also specify an element type. In this case here, I think it's 2 is a triangle and 3 is a quad. We will see. And then also you specify how many degrees of freedoms per node we will have. So in this case, as this is a scalar problem, we only have 1 degree of freedom per node. And then when you're done defining all the attributes of your element mesh, you can ask the mesh generator to create a mesh. So this is the command to do this. So meshgen.create, and that will return you chords, which is a CALFEM data structure. It will return you EDOF, which is the topology, DOFs, which is the degrees of freedom for each node. Boundary degrees of freedom is a dictionary of the marker of the markers we decided. So, for example, the line we added, we specified with 90 and 80. These can be retrieved. The degrees of freedom for those markers can be retrieved using the BDOS structure. And there's also a similar one for element markers. If you had to define special area conditions, you can get those out as well, the degrees of freedom for those areas. So then you basically do what you already did in the first exercise, or what you will do in this exercise is just do a normal CALFEM calculation here. So in this case here, I need to figure out this largest degree of freedom here. And then that I can get out from the size of the dots. You can also, then you have to extract element coordinates here with EX. You can do that with the chord extract command. And now you're ready to have to create the element stiffness matrix. And then you just loop over here. You have all the data structures to be able to assemble everything now. So now it's basically a normal finite element calculation in CALFEM. Then it's to kind of make it easier for you to assign boundary conditions. You can use special commands called apply BC. There are some other ones as well. Takes BDOFs as input, and then it takes BC and BC val as output. It will assign those, and then here you have the markers here for which boundary condition you want to assign. So in this case, I assign boundary marker 80 with 0 and boundary condition 90 with 10. And then the result will be in modified BC and BC val variables that you can feed into your solver. So in this case here, I execute my solver here, and I just provide those boundary condition here. Extract my element displacements, and then calculate my element forces here. So I calculate the flow here in this example, for example. And then there are several commands for drawing. So in this case here, I can draw the geometry, which is good to see. Before you do all this finite element, it's good to, just to get the feeling of, is the geometry okay? Then you can draw the element values, you can draw the mesh, you can draw the nodal values, add a color bar, and so on. So if you're running this standalone, you need to do this show and wait here to make sure that the windows stay on the screen. So this is the way the geometry is visualized. And this is the nodal value visualization. And here you have the max flows visualized on each element. So that is a short introduction how it works. So I will also do if I can share a different screen here. So I provided you with two notebooks here as well that you can experiment with. Now the first part here looks a bit complicated, but the problem with running in the cloud now is that I don't have the CALFEM things available, and also the mesh generation. So these lines here, they basically just install the necessary software as CALFEM, and yeah, so we will just, I have already run these, so I don't have to run them again. So here you see, the first thing I do is import my module, the geometry module, and also my mesh module, and also visualization module here. There are two modules you can use for visualization. It's the calfem.vis and the calfem.vis.mpl. So this one uses matplotlib for visualization. And if you're, it's probably the one you will use for later in the project as well. So, but there is two versions of it. I think that the vis is a bit more mature, but if you're using .vis, it will bring up windows on the screen. I will show you that in an example as well. So let's start. So the first thing we do is we define a geometry. So now I have a variable j, which I will use to define my geometry. So here I just add my points here, and those will be added in the order they are. The point command is called. And just to kind of show you how it looks, here are the. So this will be a rectangle here around here, and there will be 2 holes here inside the surface. So these points here for defining the holes. Next step, we add curves. So here you have you can create an ellipse, and then you specify the points that will make out the ellipse. So in this case here you have 7, 8. Okay. Now I'm a bit confused here. 7, 8, 9, 10. Okay, it will be yeah. At this point we will, and then we can define a spline from 0, 1. So these are the outer splines. So the lines around here, they're all called splines. And then we have a spline 4, 5, and 6. So this will be kind of a. I will run it here and see how it looks. So now we have a surface and 2 holes in it, and we need to. So now this will not mesh. So to be able to mesh it, you have to tell the mesh generator what the surface is, and that you do with here you specify the surface lines, which is so 4, 3, 2, 1, and then you specify the holes. In this case, you specify a 0.7 here, which is a hole, and then 5, 6, 0 is also a hole. So these are the lines for the holes. So now J contains all the data to create describing your geometry. So next step, we have to create a mesh generation object. So we just do that, and input is the geometry. So and this is a very convenient way. I will explain this later on for your inputs for your assignment as well, that using classes and objects enables you to kind of collect a lot of description of your problem and pass it around as a simple reference. So J here contains a lot of information, points, surfaces, lines, that makes up the geometry, and you can just pass it along like a simple variable. And then we need to have what element types we will generate. So 3 is a quad and 2 is a triangle, which is kind of odd, but that is the way GMSH works. We have only a single degree of freedom per node, and we have an element factor of 0.5. That. And then we are ready to create our mesh. Like that. And then we can visualize the geometry. We already did that, so we can skip that. We can do the mesh like this. So now all of a sudden we have all these elements. So if we look at, for example, chords. You see here that you have it's a long array of coordinates. We have here we have a topology, and we can look at the BDOFs as well. So this is dictionary here. So here you can see we defined a marker 50. It's available here. And here you see that the marker 50 contains all the degrees of freedoms that are on this line. And here you see that there is a 80 here, which is the next marker, and all its related degrees of freedom. So just to kind of illustrate what happens when you can change, for example, here. So we say we have 0.1 here. We just create a new mesh. You see here now you get a more coarse mesh. So this one controls the, so you can have 0.25 here. So you have to be a little bit careful with the scale factor, or the L size factor, because you can create huge amount of elements, and the data structures, every point will be stored in memory. So you need to, if you have millions of elements, you have to store millions of coordinates in memory on your computer, and this can be costly. So that's why it's you have to kind of start with a high value on the L scale factor and kind of scale it down to get a reasonable element size. So that was the first example. Here we have the same input here. We create a geometry. You can also set IDs of different elements yourself manually. This is something we will not probably do here. Let's see, we will create. So these are our points here. This is a bit more complicated geometry we're going to do now. So this is we're going to use real splines to control. So these points here, let's see. These points here will control the spline. So it will be kind of a, this will not part of the curve. So there will be some kind of curved thing here. We had a circle. So you see here that the circle is defined by specifying 1, 2, and 4. The points, let's see here. The 4 here is the center point of the circle. So this will define a circle between these points here. Then we add 2 splines. So the splines were from 5, 6, 7, and 5. So you have 5, 6, 7, and 5. So this is the internal spline here. And then you have the 1, 0, 3, and 2. So this will be, these are the control points controlling the curvature of the spline. And then we have to create the surface. So you have 4, 2, and I have a whole 5. And here's also where you can set your manually the curve IDs if you have forgotten to do that here. And now it's time to create a mesh again. So element type quads, and now we define that we need 2 degrees of freedoms per node. So this will be a kind of mesh problem. And then element size factor is 0.5. Create a mesh. Geometry we already showed. So what does this look like? So it's kind of a very powerful tool to generate meshes with. So let's see if we go to we're going to do a bit more complex problem, and we're going to run this without. Sorry, I have a question here in the sizes here depends on how many. Let's see here. these points here. They control the number of points on the how dense it will be. Yes, yeah. See here. Okay, so I run this in a notebook here. So this is a bit larger mesh that is moment, please. Let's see. I'll get back. I'll just draw the example how it looks like. So this mesh looks something like and it's fastened here, and you have a load, something like this, applied on the right side. So we start with importing all our necessary modules, and here I used this without MPL. So this is the we bring up standalone windows on the screen. Enable logging here is just a tool to kind of just get better logging out when you run the example. It's not something you have to implement. So here I specify all my problem parameters like T, thickness, Poisson's ratio, elastic modulus, plane stress, and then I just create my variables here, which I will need later on. So first thing, I create my geometry. And here we use a bit different approach on defining the points. So in this case here, I have a list of lists that define my points. And then I just loop over them to create the structure here in the geometry. So I call points repeatedly. Same thing here with the splines. I loop over the splines to define my points. Here I also specify the number of elements on the curve. So this would be a structured mesh to define the points. So to do the mesh generation. And here I assign markers to the different splines with the different IDs here. Just to be able to set the element boundary conditions. Here I define the circle arcs that will define the indentation of the plate. I defined a circle and loop over these circles to create the circles in the geometry. And then I create structure surfaces here, combining them together. So let's see how you can see how the geometry looks. I just copied a So let's see what happens. So this is the way the geometry looks like. So here you see that you have combined different super elements together, but the common thing is that all the elements have 4 sides. But each side can also have a so the sides can consist of a circle, line, line, line. Here as well, a circle here, line, line, and so on. Out here. So, oh, I wasn't supposed to start like that. Okay, so next step, we need to create a mesh. So I do mesh. We're using chord elements, 2 degrees of freedom, and create all our structures here. And then we will solve our problem here. First thing, we have to calculate the number of degrees of freedoms we are, so we can allocate our stiffness matrix. So we just check the size of DOFs, and then we create our element coordinates by using the chord extract function. That's a part of the CALFEM module. And then we create our global stiffness matrix, loop over elements here. Then we need to solve our equation system. And here we need to specify BC and BC val, because we will add, you could have skipped the val here as well, but I think the command will require you to have both of these here defined. So on our marker 5, we will apply fixed boundary conditions. And here you can specify, if you put the last parameter here, see if we can just see what. So if you look here, you have the boundary DOFs, which is the data structure from our mesh generation. BC is our boundary conditions, degrees of freedom that we want to modify. 5 is the marker, and then we have the value, and we have the dimension here. And the dimension controls, if you want to, 0 means that you have put the value 0 on both dimensions. So if you have 2 degrees of freedoms, both of them will be described or prescribed. If you put 1, you will have applied to the X degree of freedom, and 2 to the Y degree of freedom. And then we also have an apply force, which is a special command to apply forces to the force vector. And then we solve our equation system. We extract the element forces here using the extract LDISP. And we calculate our von Mises stresses here by looping over each element and calculating the element stresses and strains, and then calculating the Mises stresses to visualize those. And then we use the visualization commands here to actually visualize all of this. So if we run everything here, we just remove this. So now you see that you will have this is the deformed element mesh. You have the effective stresses here, the geometry. I don't think we have more on that. No, as output. So I think you can also zoom in like this to look at it in close up. Same thing with this one here. And here you can also see that when you are running the CALFEM program here, it will call GMSH underneath here. So it will actually go out and look for a program that has GMSH and generate input for that program, read the output, and then use that later on. So it's the mesh generation is implemented by calling GMSH the application. So if we do a short break here, 15 minutes, and then in the final part I will discuss the assignment and the conceptual thoughts about how you should structure your code and why we do the things we do in the worksheets. So I will get back in 15. Okay, let's restart. I will start from the beginning here. Okay, so now I shouldn't be muted anymore, I hope. No. So yeah, to rewind a bit from my talk here, the finite element code is usually divided into three parts. You have a input, which defines the your coordinates, your nodes, your elements, your material properties, anything that defines your model on a high level. Then you have a solver that takes you the input and solves the finite element problem, and then you have output that is generated from the solver. And from that, you probably need to do some kind of you need to create a some kind of report. You probably would like to do some kind of visualization. So you want to have a screen here. You want probably to look at your data somehow and have some stresses displayed on it. So that has to be generated as well. So these are the parts. So if you do an object-oriented analysis here, there are some nouns we can identify here. So we have the input here, we have a solver, we have an output, we have a report, and we have a visualization or something like that. So visualization. So to take this and to do classes, we create for the input, we can create input data. We have our solver. We put that here in the middle here. This is also a class. And we have output data. We have a report. and we have a visualization. So the idea here is that if we instantiate objects on these, the solver will have a reference to, we'll assign a reference to input data. We also have a reference to output data. So by assigning input data and output data to the solver has all the information to actually perform the finite element calculation and store the results in output data. The report is also can be a separate class that we use later on, but the report will also have access to the output data. It will also have access to the input data. And from these two, this report class object can generate a report. The visualizations is the same thing here. It will also have access to input data and output data. So the information carrying structures objects we will use is the input data and output data. And the nice thing we're having this approach is that you could, for example, create multiple instances of input data. So if you want to do a parametric study, for example, you just create a lot of these input data objects, and then you can loop over them. And just when you want to solve, you just assign a reference to this input data to the solver. And the solver won't notice any difference, it will calculate. And then the same thing, you can have multiple output data objects that store the output data for each of the examples. So in this way, it's very easy to convey information between in your program in an easy way without passing a lot of variables. So the objects will be the information carriers in the system. So let's see here. So how can this be implemented in code? Let's see if we can share again. So this is you get some hints here on how to create your program here, but I think it's on a very high level. So in this, sorry, in this example here, I have my main program, or I have a module called stress model, which is implements the stress model problem. I have all my input here, and here you see the classes I have defined. So I have a class for input data, class for output data, a class for my solver. I have a report class and a visualization class. So in my main program, the first thing I do before I actually calculate is I create instances of my input data and my output data. So input data could also be read from file, which we will be doing, and also saved to file. And when I have my input data, when I create my solver instance, I pass them along into the solver class when I create that object. So now the solver has access to references to input data and output data. So it knows where to read the input data and write it output data too. And then I have a method called execute, which will execute my solver, and the solver will then populate the output data structure here with information. And then I have some other things here as well. And you see also here that you can, the visualization will also take input data and output data and display the element meshes and so on. So you see that the programming is quite manageable when you have this kind of structure. So the input data will contain a lot of things. So if you say right here, input data dot okay. Okay, let's see if I run this here just to. So now I will run my solution here. So if I look at the variable explorer here, let's see if we can find input data. So in input data, you will have there's a lot of variables here. E, A, B, B, C. So you see, it's very to kind of feed that into the solver in an easy way would be quite complex. So in this case here, you can in a very simple way just move all your problem information around in your program in a very easy way. And another thing you can do is, for example, you could do and I'm going to do illustrative example. So if I create here data equals an empty list like this, I can do I populate it for I in range 10, and I create input data to its data. And then I can append this to the param data here. This. So now I create them, and these could read. You can modify those, and you can specialize these classes to have different areas. You can also specify different parameters. For example, you could have input data dot. I'm not sure. We have the parameters here. Let's see. A. So for example, I can set the value A on input data here to change a different parameter and vary that along the line, along the parameters here. Then I can do like this. I can do for input output and then you can do like this. So we have create a solver object here. We already have a solver, so we can do so by these lines here, I have created a parametric solver in a very easy way. I vary my A parameter, and then I just calculate over and over again by changing the input data and output data to my solver and just executing it. So this is the way you should think about this, that when you create classes, you can kind of create information bearers that contain information which you can pass along in your program. And that will be also more important when you do user interfaces, that you often want to separate the user interface code from your model code, and then you want to be sure that it's easy to handle even a complex model in your user interface without mixing finite element code with user interface code. And using input data and output data will be a very easy way. You just have to have one single reference in your user interface code to your finite element input data. Same thing with output data and your solver. Easily it will be maintainable in that way. So I think that was the whole idea of explaining this. So you have any questions on this, or does it make any sense, the ideas I have presented here? So I'm just open for questions now. So I have a questions here regarding geometry. In the user interface we are going to design, we are not going to do a complete geometric editor in that sense, so the user can specify elements. So the user interface will be using our parameters. So for example, the width and height of a geometry, the width of your slot in your groundwater problem, or depth. So the input in the user interface will be on a higher level than the geometry. So the geometry will be generated from the input parameters in the model. And so the users or the code we produce for the user interface in this course, if you follow the worksheets, are limited. So the user can only specify the parameters of your model in that sense. But if you're into, you could do a graphical editor as well, or you can do a user interface where the user can specify points, lines, and so on. So yes, so the base geometry is fixed. So you have a model of a parametric model where they can change. Yeah. Otherwise, this course can be very complex if you also should implement basic CAD systems for defining your geometry. But I had last year, there were some students that actually imported geometry from a CAD system and used that as the geometry in this application. And then they could, the user could provide boundary condition on that CAD model. So that is also something you could consider if you want to do some more extensions on this project assignment. Okay, I will be. I'm available on Canvas if you have any questions. There is a final thing with the hand-ins, because I'm also quite new on Canvas. There is a really nice tool for commenting code, which is called SpeedGrader, which I just missed when I told you to submit zip files. I would appreciate if you can submit your Python files individually. Because then it's much easier for me to comment them. Otherwise, I have to extract them and comment them and add them to the comments. Also, when the grading I've done so far, the comments are inside the files. So there is a tool you can get the comments from inside each file. So try to submit them as separate Python files. Or if you have any input files, provide them also separately. Then it's much easier for me to comment and grade. Okay. Okay. Otherwise, we see there is an exercise tomorrow in the afternoon, and I will be there then, so you can ask more questions then. You don't have to resubmit your old assignment. You can upload several files to each assignment. Now I think there should be no perhaps there is an upper limit, but I think there should be enough for this assignment. Okay then. See you tomorrow then.